There is something about the surface of the ocean at night that suggests a kind of boundary, not between water and air exactly, but between what can be known from where we stand and what remains perpetually out of reach, hidden beneath a darkness that begins just below the place where the last ripple fades. The wind moves across it slowly, carrying salt and coldness, and if you were to stand at the edge of such a place in the hours before dawn, you might notice how the water holds light differently than the sky does, refusing it almost, or swallowing it so completely that even the moon's reflection seems like a small concession to the visible world. This is the feeling of standing above something enormous, something that does not announce itself but simply waits, patient and unrushed, in a stillness so deep it borders on the geological. If this kind of quiet reflection helps you unwind, you can subscribe to Quiet Science and continue this journey with us, slowly descending through ideas that don't demand attention, but offer it, like dim lights along an unfamiliar path. What lies beneath the surface is not simply more water, though that is the easiest way to describe it. It is a second world, inverted and lightless, where the rules that govern our experience on land become suggestions at best, and where distance is measured not in miles, but in the accumulation of pressure, the fading of color, the absence of sound as we understand it. To ask about the depth of the ocean is not to ask for a number, though numbers exist. It is to ask what it means for something to be so far below that it exists almost in another dimension of time, where a single journey down takes hours, and the return, if it happens at all, feels like surfacing from a dream you cannot quite remember. When you look at the ocean during daylight, what you see is mostly a reflection of the sky, a surface that acts like a mirror tilted at an angle, showing you clouds and blue and the movement of air more than it shows you water. But at night, when there is no sky to reflect, the ocean reveals something closer to its actual nature. It becomes a plane of near total opacity, a threshold beyond which vision simply stops. This is not because the water itself is dark, though it appears that way, but because light, which travels so effortlessly through air, struggles to penetrate even a few meters into seawater before being absorbed, scattered, converted into heat and nothingness. What this means, in practical terms, is that the ocean is not a single thing but a series of descending environments, each one darker and stranger than the last, stacked vertically like floors in a building where every floor is more isolated than the one above it, until eventually you reach depths where the concept of light becomes almost theoretical, a memory of the surface world that no longer applies. Human beings have always been creatures of the surface, not just in the literal sense, but in the cognitive sense as well. We understand distance horizontally. We know what it means to walk a mile, to drive across a continent, to fly from one city to another. But vertical distance, especially downward, carries a different weight. To descend is to move against the pull of return, to enter a space where the possibility of coming back becomes less certain with every meter. The ocean amplifies this feeling because it offers no landmarks, no fixed points of reference, only a gradient of increasing darkness and pressure that transforms gradually enough that you might not notice the change until you realize you can no longer see the surface, can no longer tell which direction is up except by the pull of your own buoyancy. There is something profoundly disorienting about this, and yet also strangely calming, as if the absence of reference points allows the mind to stop trying to orient itself and simply exist within the descent, suspended in a medium that holds you without effort. The first truth about depth is that it is vast in a way that resists easy comprehension. The average depth of the ocean is around 3,800 meters, which is to say that if you could drain all the water and walk across the ocean floor, you would find yourself moving through a landscape of plains and mountains and valleys, where the vertical distance from the lowest point to the highest is greater than the height of any mountain range on land. Mount Everest, measured from sea level to summit, rises about 8,800 meters. The Mariana Trench, measured from sea level downward, descends nearly 11,000 meters. If you were to place Everest at the bottom of the trench, its peak would still be covered by more than 2 kilometers of water, a detail that feels almost absurd until you sit with it long enough to realize that it suggests something fundamental about the planet's architecture, that the ocean is not a shallow coating on the surface of the Earth, but a geological feature as significant as the continents themselves, a second terrain that exists in permanent shadow. And yet, for all its size, the ocean does not feel vast when you are on it. From a boat, the horizon curves gently in all directions, but it is a near horizon, only a few miles away, giving the impression of intimacy rather than scale. The vastness is hidden, folded downward into a dimension that cannot be seen from above, only inferred. This is part of what makes depth so difficult to grasp. It does not present itself visually. You cannot stand at the edge of the continental shelf and look down into the abyss the way you can stand at the edge of the Grand Canyon and see its depth laid out before you. The ocean keeps its depth private, reveals it only to those who descend into it, and even then, only a few meters at a time. As visibility collapses and the water closes in around you like a curtain drawn slowly shut. What pulls a person toward depth, whether physically or imaginatively, is not the promise of discovery, though that is often the reason given. It is something older and less rational, a need to confirm the boundary of the known, to find the edge of the map and see what lies beyond it. The ocean offers this in a way that few other places on Earth still can. We have mapped the surface of Mars in higher resolution than we have mapped the ocean floor. We have sent robots to the edges of the solar system, but the deepest parts of the ocean remain largely unexplored, not because they are unreachable, but because reaching them is difficult and expensive and yields information slowly in small increments, without the drama of a flag planted or a horizon crossed. The ocean does not reward speed. It rewards patience, and perhaps that is why so few have gone, and why those who do return changed, speaking of silence and pressure, and a darkness that feels less like an absence of light, and more like a presence of its own. To understand depth, you must first accept that it is not a distance you can walk. It is a threshold you cross by letting go of the surface, by allowing yourself to sink, trusting that the water will hold you even as it presses inward from all sides, slowly, incrementally, until the pressure becomes something you feel not just on your skin, but in your chest, in your ears, in the hollow places inside your body where air used to be. And at some point, if you go far enough, the question stops being how deep you can go and becomes instead how long you can remain, suspended in the cold and the dark, before the need to return to the surface becomes overwhelming, before the weight of all that water above you reminds you that you are a visitor here and not a permanent resident. Light, when it enters water, does not simply continue in a straight line the way it does through air. It bends, scatters, refracts against particles suspended in the water column, plankton, sediment, organic debris, and begins almost immediately to lose energy, to be absorbed by the molecules of water itself, which are not as transparent as they appear from above. What this means is that the ocean is not evenly lit, not a bright space that gradually dims with depth, but rather a series of zones defined by how much sunlight can penetrate them, each zone representing a different relationship to the surface, a different degree of separation from the world above. The first of these zones, the one you enter as soon as you submerge, is called the epipelagic zone, though that name feels too clinical for what it actually is, a band of water from the surface down to about 200 meters, where sunlight is still strong enough for photosynthesis to occur, where the water holds warmth and color and movement, where most of the life we think of as oceanic lives and feeds and reproduces in relative brightness. But even within this zone, light is already changing in ways that are invisible to human perception unless you know to look for them. The first color to disappear as you descend is red, which vanishes almost immediately, within the first 5 to 10 meters, absorbed by water molecules so efficiently that red objects, a red wetsuit, a fish with red markings, blood, begin to appear gray or black even in what seems like full daylight. Then orange fades, then yellow, each wavelength of light surrendering its energy to the water at a different rate, absorbed selectively based on the physics of how electromagnetic radiation interacts with H2O. By the time you reach 30 meters, the world has shifted entirely into blues and greens, the only colors capable of penetrating this far, and even they are dimmer than they were at the surface, filtered and softened until the light feels diffuse, as if it is coming from everywhere and nowhere at once. This is a subtle thing, easy to miss if you descend slowly, because your eyes adjust as you go, compensating for the loss of brightness without you realizing it. But if you were to pause at 30 meters and look up toward the surface, you would see something that might surprise you. A ceiling of light, a kind of inverted sky that glows faintly above, growing more distant with every meter you descend, until eventually it becomes a memory of brightness, rather than brightness itself. What you are witnessing is the boundary of the photic zone, the region where sunlight is strong enough to matter, where plants can still grow and the energy of the sun still drives the chemistry of life. Below this boundary, the rules begin to change. Below this boundary, the ocean becomes something fundamentally different from what it is near the surface. The transition is not sharp. There is no line you cross where suddenly all light vanishes. Instead, there is a gradient, a twilight zone, that extends from around 200 meters down to about 1,000 meters, where light exists but only barely, where the sun's influence weakens meter by meter until it is reduced to a faint blue glow, the last remnant of surface brightness filtering down through hundreds of meters of water. This is the dysphotic zone, the twilight realm, and it is one of the most psychologically disorienting parts of the ocean because it exists in a state of permanent ambiguity. Not quite light, not quite dark, but something in between. A perpetual dusk that never resolves into day or night. If you were to descend through this zone, you would experience a kind of slow sensory deprivation, a gradual withdrawal of visual information that forces the mind to rely more and more on other senses, on the feel of water pressure against your skin, on the sound of your own breathing, on the awareness of your body as a small, warm object suspended in an enormous cold space. It is worth pausing here to consider what this means for the creatures that live at these depths. They are not blind, most of them, but their vision is adapted to detect the faintest traces of light, the dimmest flickers of bioluminescence, the subtle differences in shadow that might indicate the presence of prey or predator. Their eyes are often enormous relative to their body size, designed to gather as much light as possible from an environment where light is scarce, where a single photon can mean the difference between finding food and starving. Some species have evolved eyes that point upward, scanning the faint glow of the surface for the silhouettes of other fish, using the last remnants of sunlight as a kind of backlight against which movement can be detected. This is called counter-illumination hunting, and it works only in the twilight zone, only in that narrow band of depth where there is still just enough light to cast a shadow, but not enough to see clearly. What happens then, when even that faint light disappears? What happens at the depth where the last blue photon is absorbed, where the sun's reach finally ends and the ocean becomes truly, absolutely dark? This is not a question that can be answered in meters alone, because the precise depth at which light vanishes depends on the clarity of the water, on the angle of the sun, on the season, and the latitude and the amount of sediment in suspension. In the clearest parts of the open ocean, light might penetrate as deep as 1,000 meters before being extinguished completely. In murkier coastal waters, darkness might begin at 300 meters or less. But regardless of where the boundary falls, the result is the same: a transition from a world where light exists, however faintly, to a world where it does not, where the concept of vision as we understand it becomes irrelevant, where sight is replaced by other forms of sensing, by bioluminescence and chemical detection, and the ability to feel vibrations in the water that might indicate movement nearby. And this is where the ocean truly begins to feel alien, not in the sense of being hostile or dangerous, though it is both, but in the sense of operating according to principles that are so far removed from surface life that they require a different vocabulary to describe. The darkness is not empty. It is full of life, full of activity, full of organisms that have found ways to thrive in conditions that would kill most surface creatures within minutes. But it is a life that happens slowly, quietly, without haste, because energy is scarce and movement is expensive, and every calorie must be conserved. Pressure, unlike light, does not disappear as you descend. It accumulates. It builds with every meter, steadily, predictably, adding weight in a way that is so gradual you might not notice it at first, especially in the shallower waters, where the increase is gentle and the human body can still adapt without much difficulty. But pressure is always there, always pressing inward from all directions simultaneously. And what it represents is not some abstract force, but something concrete and measurable. The literal weight of all the water above you, stacked column upon column, compressing downward under the pull of gravity. At the surface, you experience roughly 1 atmosphere of pressure, which is the weight of all the air above you, pressing down at about 14.5 pounds per square inch. It is so constant, so evenly distributed, that you never feel it as pressure at all, only as the neutral baseline of existence. But water is much denser than air, roughly 800 times denser, which means that for every 10 meters you descend into the ocean, the pressure increases by approximately 1 atmosphere. At 10 meters you experience 2 atmospheres of pressure, one from the air above the water, one from the water itself. At 20 meters, 3 atmospheres. At 100 meters, 11 atmospheres. The progression is linear, unrelenting, and it continues all the way to the bottom. What this means, in terms that matter to a body made of flesh and bone and air spaces, is that pressure becomes the dominant fact of depth, more significant even than darkness, because pressure is what determines whether you can survive in a given environment, whether your lungs can expand, whether the gases dissolved in your blood will remain dissolved or come out of solution and form bubbles that block your circulation, whether the air cavities in your ears and sinuses will compress painfully or rupture entirely. Human beings are not well suited to pressure. We are creatures built for 1 atmosphere, for the surface world, and our bodies contain too many compressible spaces: lungs, sinuses, the middle ear, the air-filled cavities within bones that respond badly to compression. A free diver, descending on a single breath, can reach depths of 100 meters or more, but only because they have trained their bodies to tolerate the compression, to equalize the pressure in their ears and sinuses, to allow their lungs to collapse inward as the surrounding pressure increases, shrinking to a fraction of their normal volume. And even then, they can stay only briefly, a few minutes at most, before the need for oxygen pulls them back toward the surface. For those who wish to go deeper, the solution has always been to bring the surface with them, to enclose themselves in a rigid shell, a submarine, a diving suit, a pressurized capsule that resists compression and maintains an internal atmosphere close to surface pressure. But this creates its own problems, because now the boundary between the inside and the outside becomes a point of tremendous mechanical stress. The hull of a submarine must be thick enough, strong enough, to withstand the pressure differential without collapsing. And the deeper you go, the thicker the hull must be, until eventually the weight of the hull itself becomes prohibitive, a limiting factor that determines how deep is too deep. The bathyscaphe Trieste, which descended to the bottom of the Mariana Trench in 1960, had walls several inches thick and carried ballast made of iron pellets just to sink against its own buoyancy. When it reached the bottom, at a depth of nearly 11,000 meters, the pressure outside was over 1,000 atmospheres, more than 8 tons per square inch, enough to crush almost any material, to compress steel like putty, to turn wood into a dense, waterlogged mass that bears little resemblance to its original form. And yet, life exists at these pressures. Not human life, obviously, but bacterial life, microbial life, and even complex multicellular organisms, fish, crustaceans, worms, that have adapted to conditions we would consider incompatible with biology. The key difference is that these organisms do not have air spaces. Their bodies are composed mostly of water and tissue that is already incompressible, that does not collapse under pressure because there is nothing to collapse. The pressure outside their bodies equals the pressure inside, a state of equilibrium that eliminates the stress of compression. Their cell membranes are reinforced with specialized lipids that remain flexible under pressure. Their proteins are structured in ways that prevent them from denaturing, from unfolding and losing function the way surface proteins would. They have, in effect, solved the problem of pressure by becoming pressure neutral, by building themselves out of materials that do not care how many atmospheres are pressing down on them. This is a profound adaptation, one that required millions of years of evolution to achieve. And it suggests something important about the nature of depth, that it is not an obstacle to life, but simply a different set of conditions, a different baseline to which life can adapt if given enough time. The organisms that live in the deep ocean are not struggling against pressure. They are living within it, comfortably, in the same way that surface organisms live within one atmosphere without ever thinking about it. If you were to bring a deep-sea fish to the surface, it would not survive, not because the lack of pressure would kill it directly, but because its body is calibrated for high pressure, and the rapid decompression would cause its swim bladder to expand, its tissues to rupture, its internal chemistry to fail. In a very real sense, these creatures are as alien to the surface as we are to the depths, separated by a pressure gradient that is as effective as any physical barrier. But pressure does more than just determine what can live where. It also changes the properties of water itself, making it denser, changing how sound travels through it, altering the solubility of gases, affecting the rate of chemical reactions. At the deepest parts of the ocean, water is compressed to the point where it is noticeably denser than surface water, though it is still liquid, still capable of flowing and mixing, still recognizable as water, even if its behavior is slightly different. This has consequences for ocean circulation, for the way currents move, for the distribution of heat and nutrients, all of which depend on the subtle interplay between temperature, salinity, and pressure at different depths. The ocean is not a uniform body of water, but a layered system stratified by density, and pressure is one of the forces that maintains those layers, that keeps deep water deep and surface water at the surface, preventing them from mixing easily. To descend, then, is not just to move through space, but to move through increasing pressure, to enter regions where the weight above becomes so great that it begins to define the environment more completely than any other factor, where pressure is not something you experience occasionally, as a tightness in your ears or a change in buoyancy, but something constant and omnipresent, a force that shapes everything, from the chemistry of seawater to the architecture of living cells, from the design of submersibles to the very possibility of human presence. Below 1,000 meters, you enter what oceanographers call the bathypelagic zone, though a more intuitive name for it might simply be the midnight zone, because that is what it is, a region of perpetual midnight, where the sun has no influence whatsoever, where darkness is not the absence of light, but the default state, the baseline from which all other conditions are measured. This is not the darkness of a moonless night on land, where your eyes eventually adjust and you begin to pick out shapes and silhouettes against a slightly less dark sky. This is absolute darkness, the kind that does not diminish or soften with time, the kind that presses against your eyes like a physical presence, where looking and not looking produce exactly the same result. If you were to descend into this zone without artificial lights, you would be functionally blind, unable to see your own hand held directly in front of your face, unable to distinguish up from down except by the pull of gravity or the sensation of water pressure increasing as you sink. And yet, even here there is light, though not sunlight. It comes from the organisms themselves, from the chemical reactions occurring within their bodies, reactions that produce photons as a byproduct, a phenomenon called bioluminescence that is so common in the deep ocean that some scientists estimate up to 90% of deep-sea creatures possess the ability to generate their own light. This is not light in the way we experience it on the surface, not bright or warm or continuous, but rather light as punctuation, as brief flashes and glows and pulses that serve specific purposes: communication, camouflage, predation, mating. A jellyfish might pulse with blue light as it drifts through the water column, a signal to potential mates or a warning to predators. A squid might emit a cloud of luminescent bacteria when threatened, creating a glowing decoy that distracts attackers while it escapes into the darkness. An anglerfish might dangle a bioluminescent lure in front of its mouth, a tiny glowing orb suspended on a modified spine, waiting patiently for smaller fish to approach, mistaking the light for food or safety. The chemistry of bioluminescence is elegant in its simplicity. It requires only two components: a light-emitting molecule called luciferin and an enzyme called luciferase that catalyzes the reaction. When luciferin reacts with oxygen in the presence of luciferase, it produces light, usually blue or green, because those wavelengths travel farthest in seawater, penetrating the darkness more effectively than red or yellow, which are absorbed almost immediately. Different organisms have evolved different variations of this basic chemistry, some producing light within specialized cells called photophores, others harboring symbiotic bacteria that glow continuously in exchange for nutrients and shelter. The result is a kind of living constellation, a sparse scattering of lights in the darkness that moves and shifts and responds to stimuli, creating patterns that might seem random to a human observer, but are in fact highly structured, full of information that other deep-sea creatures can read and interpret. What makes bioluminescence so remarkable is not just that it exists, but that it evolved independently dozens of times, in jellyfish and fish and squid and shrimp and bacteria, in lineages separated by hundreds of millions of years of evolution, all arriving at the same solution to the problem of darkness. This suggests that light, even in tiny amounts, confers a significant survival advantage in the deep ocean, enough of an advantage that natural selection has repeatedly favored organisms capable of producing it. And this makes sense when you consider how difficult it is to find food or mates, or avoid predators in total darkness, how disorienting and dangerous the environment becomes when you cannot see. Bioluminescence restores a degree of visual awareness, not enough to navigate continuously or to see distant objects, but enough to detect movement, to identify potential threats or opportunities, to communicate across short distances without sound. There is a layer within the midnight zone, usually between 200 and 1,000 meters, where bioluminescence is particularly concentrated, a region known as the deep scattering layer because it was first discovered by sonar operators during World War II, who noticed a layer of the ocean that reflected sound waves as if it were the seafloor, except it was too shallow and it moved, rising toward the surface at night and sinking deeper during the day. What they had found was not a geological feature, but a biological one, a vast aggregation of small marine animals, mostly zooplankton and small fish, that migrate vertically every day, ascending at dusk to feed in the plankton-rich surface waters and descending at dawn to avoid predators that hunt by sight. This is the largest migration on Earth in terms of biomass, involving billions of organisms moving up and down through hundreds of meters of water every single day, and much of it happens in complete darkness, guided by internal clocks and sensitivity to the faint light levels at the boundary of the twilight zone. If you were to dive through this layer at night, you would encounter something surreal, a kind of underwater snow, except instead of frozen water falling downward, you would see tiny glowing particles moving upward, millions of small creatures drifting past you in the darkness, each one emitting brief flashes of blue-green light as they pass. It would feel less like descending through water and more like descending through a galaxy, a three-dimensional space filled with distant stars that wink on and off, that appear and disappear with no apparent pattern, creating an illusion of depth and motion that is difficult to process because your brain has no reference point, no way to judge distance or size or speed in the absence of ambient light. And beneath you, below the migrating layer, the flashes become sparser, more isolated, spread out over greater distances, until you are moving through a darkness punctuated only occasionally by brief bursts of light, each one marking the presence of a creature going about its business, hunting or fleeing or simply drifting with the current, alone in a darkness that extends in all directions for hundreds of meters. What does it mean to live in such a place, where light is not a constant but an event, where seeing happens only in flashes, where the environment offers no landmarks, no fixed points, no way to orient yourself except by instinct and memory? It means that life becomes a kind of meditation, a state of waiting punctuated by brief moments of action, where most of the time is spent conserving energy, drifting slowly through the cold, waiting for food to appear or for a mate to signal its presence. with a pattern of flashes that only members of the same species can recognize. One of the difficulties in understanding depth is that the human mind is not particularly good at visualizing large vertical distances. We can imagine walking across a city, can picture the distance between buildings or neighborhoods, can grasp the scale of horizontal space because we move through it constantly, because it is familiar and mappable and broken up by landmarks that give us reference points. But vertical distance, especially downward, exists mostly as abstraction. We know tall buildings by their floor numbers, mountains by their elevation, but these remain numerical concepts rather than felt experiences. Because most of us will never climb to the top of a skyscraper or scale a mountain, we'll never experience those heights directly except through windows or photographs. The ocean asks us to reverse this already difficult intuition, to imagine not height but depth, not climbing upward but sinking downward, and to do so in an environment that offers no visual cues, no floors or levels or marked intervals, only an increasing pressure and an increasingly total darkness. Perhaps the most common way to grasp oceanic depth is through comparison with mountains. By taking the vertical distances we associate with the highest peaks on Earth and inverting them, placing them beneath the surface instead of above it. Mount Everest, standing at 8,849 meters above sea level, has become the default reference point for scale, the mountain against which all other heights are measured. But if you were to somehow lift Everest from the Himalayas and lower it gently into the deepest part of the ocean, the Challenger Deep, in the Mariana Trench, the summit would come to rest more than 2 kilometers below the surface. The entire mountain, peak to base, would be submerged, covered by water, with room to spare. This is not a metaphor. This is a simple statement of relative measurements, and yet it feels impossible, almost offensive to common sense, because Everest is so firmly associated with the idea of ultimate height, with the edge of the breathable atmosphere, with the limit of human endurance, that imagining it underwater, invisible, irrelevant to the surface world, requires a mental adjustment that most people find difficult to make. But even this comparison understates the scale, because Everest is a single peak, a singular feature in a landscape that also includes valleys and plateaus and foothills. The ocean floor, by contrast, is an entire landscape, complete with plains and ridges and mountains and trenches, all of it existing beneath thousands of meters of water. The mid-ocean ridges, the underwater mountain ranges that run like seams through the major ocean basins, rise several kilometers above the surrounding seafloor, yet remain completely submerged, invisible from the surface, unknown to most of human history. The Hawaiian Islands, which appear from sea level as isolated volcanic peaks rising out of the ocean, are actually the exposed summits of massive undersea mountains whose bases rest on the ocean floor more than 5 kilometers below the surface. If you measure these mountains from base to summit, several of them are taller than Everest, taller than any mountain on land, but because most of their height is hidden beneath water, they do not register in our intuitive sense of scale, do not appear in lists of the world's tallest mountains, exist only as footnotes in discussions of extreme topography. What this reveals is that the ocean floor is not flat, not a featureless plain, but a landscape as complex and varied as any on land, with mountain ranges that dwarf the Alps, canyons that make the Grand Canyon seem modest by comparison, plains that stretch for thousands of kilometers without a significant change in elevation. The difference is that all of this exists in permanent darkness, under pressures that would crush most surface materials, in an environment so remote and inhospitable that it has been explored less thoroughly than the surface of the Moon. We have better maps of Mars, in fact, than we have of the ocean floor, not because Mars is easier to study, but because it can be photographed from orbit, because light reflects off its surface and returns to cameras and sensors in ways that water simply does not allow. The ocean keeps its topography hidden, reveals it only through sonar mapping, through sound waves sent down from ships and reflected back, measured in milliseconds, converted into depth readings that accumulate slowly over years of systematic survey work. And even when we do map the ocean floor, what we find is difficult to relate to the lived experience of depth. A bathymetric map shows contours and colors, blue gradients indicating different depths, but it does not convey what it would feel like to descend through those depths, to pass through the twilight zone and into the midnight zone, to continue sinking through the bathypelagic zone and into the abyssal zone below, where the pressure is measured in hundreds of atmospheres and the temperature hovers just a few degrees above freezing year-round. The map shows the Mariana Trench as a narrow depression, a crescent-shaped scar in the ocean floor, but it does not show the psychological weight of being in such a place, of knowing that you are beneath 7 miles of water, that the surface is farther away than many people will travel in a day's drive, that if something goes wrong, there is no possibility of rapid ascent, no chance of swimming to safety, only the slow mechanical process of returning to the surface in a pressurized capsule, hoping that the equipment does not fail, that the hull does not crack, that the ballast releases properly and the buoyancy calculations were correct. Scale, in other words, is not just a matter of numbers. It is a matter of comprehension, of finding ways to make large distances feel real and present rather than abstract. And the ocean resists this kind of comprehension because it hides its scale, because you cannot see to the bottom, cannot look down and judge the distance the way you might look up at a mountain and estimate how far it is to the summit. The ocean's depth is invisible, inferred rather than observed, and this makes it easier to forget, easier to treat the ocean as a surface feature, a two-dimensional plane across which ships move, rather than as a three-dimensional volume, a second world stacked vertically beneath the one we inhabit, containing more space, more topography, more potential habitat than all the continents combined. Below 4,000 meters, the ocean floor begins to flatten, spreading out into what are called the abyssal plains, though the word plain does not quite capture the scale or the character of these regions. They are among the flattest places on Earth, vast expanses of sediment that stretch for hundreds or thousands of kilometers, with almost no change in elevation, no hills or valleys or significant features, just an endless horizontal surface interrupted occasionally by isolated seamounts or the scattered remains of undersea volcanic activity. If you were to descend to the abyssal plains and somehow maintain visibility, which you cannot because the darkness is absolute, you would see a landscape that resembles nothing so much as a desert, though instead of sand there is mud, a fine-grained sediment composed of the remnants of countless organisms that lived and died in the waters above, their bodies slowly drifting downward through the water column over weeks or months, settling finally on the ocean floor where they accumulate at a rate measured not in meters per year, but in centimeters per 1,000 years, sometimes less. This mud is called pelagic sediment, and it is one of the primary records of Earth's biological and geological history, a layered archive that stretches back millions of years in places, each layer representing a different era, a different climate, a different configuration of ocean currents and atmospheric conditions. The sediment consists mostly of calcium carbonate from the shells of foraminifera and coccolithophores, microscopic plankton that build protective casings around themselves and then die, sinking slowly through the water until they reach the bottom, where they join the accumulating layers of older shells, older organisms, compressing gradually under their own weight into a soft ooze that covers the abyssal plains like a blanket. In some regions, particularly beneath the most productive surface waters, the sediment also contains silica from diatoms and radiolarians, single-celled algae and protists whose glass-like skeletons contribute to a different kind of ooze, one that feels slightly grittier, slightly less fine than the carbonate mud, but which serves the same function, preserving a record of life lived in the sunlit layers far above. The rate of accumulation is almost impossibly slow, difficult to comprehend in human terms. A layer of sediment 1 centimeter thick might represent 1,000 years of continuous deposition, which means that if you were to dig down just 1 meter into the abyssal mud, you would be looking at sediments that were deposited over the course of 100,000 years, a span of time that includes the entire recorded history of human civilization, and then stretches back further, into the ice ages and beyond. And the sediment does not stop at 1 meter. In some places, it extends down hundreds of meters, accumulating since the ocean basin first formed, since the continents drifted into their current positions, since the last major reorganization of Earth's tectonic plates. To stand on the abyssal plains, if you could stand there, if the pressure were not so great and the darkness so complete, would be to stand on a surface that is constantly, imperceptibly growing, rising upward at a rate too slow to measure directly, visible only when viewed across geological timescales, across millions of years of continuous sedimentation. And yet, for all its stillness, the abyssal plain is not lifeless. There are organisms here, though they are sparse, scattered across the sediment at densities far lower than anything you would find in shallower waters, where food is more abundant and energy more readily available. The creatures that live on the abyssal plains are mostly small: sea cucumbers, brittle stars, tiny crustaceans, polychaete worms, moving slowly across the mud or burrowing into it, feeding on the organic particles that settle from above, on the marine snow that drifts down continuously, but in such small quantities that it barely sustains them. These organisms have adapted to live on almost nothing, to survive on energy budgets so constrained that most of their time is spent motionless, conserving calories, waiting for the next small influx of food to arrive. They grow slowly, reproduce infrequently, live for decades or longer in some cases, because growth and reproduction are expensive and energy is scarce, and there is no evolutionary advantage to haste when the environment changes so little over the course of a lifetime. The abyssal plains exist in a state of near-perfect stability, a constancy that is difficult to find anywhere else on Earth. The temperature is almost uniform, hovering between 1 and 4 degrees Celsius year-round, never warming, never freezing, maintained at this narrow range by the circulation of deep ocean currents that move slowly through the ocean basins, carrying cold water from the polar regions toward the equator and back again in a cycle that takes centuries to complete. The pressure is constant, never fluctuating, always enormous, but always the same. The darkness is absolute and unchanging, unaffected by the day-night cycle at the surface, unaffected by seasons or weather, simply dark in the same way that space is dark, because there is no source of light nearby and no possibility of one appearing. And the sediment continues to accumulate, slowly, steadily, covering everything, smoothing out irregularities, filling in depressions, creating a landscape that is gradually, incrementally flattening itself into a perfect plane. What this means is that the abyssal plains operate on a different sense of time than the surface world does. On land, we experience time as a sequence of events: days and nights, seasons, storms, droughts, the growth and decay of vegetation, the movement of animals, the constant reshaping of the landscape by wind and water and ice. But on the abyssal plains, time is measured in the slow accumulation of sediment, in the gradual migration of organisms across the seafloor, in the occasional disturbance caused by a turbidity current or a submarine landslide, events that happen so infrequently they might occur only once in 1,000 years, once in 10,000 years, leaving behind traces that persist for millennia because nothing else happens to erase them. The abyssal plains are a place where geological time becomes visible, where the processes that normally operate too slowly to observe directly are the only processes that matter, where change happens, but so slowly that it appears, from any human perspective, as stillness. And perhaps this is what makes the abyssal plains so difficult to think about, so hard to hold in the mind. Not their size, though they are vast, and not their depth, though they are deep, but the way they collapse the distinction between motion and stillness, between life and geology, between time as we experience it and time as the planet experiences it, stretched out over durations so long that human lifetimes become rounding errors, irrelevant blips in a process that has been underway for millions of years and will continue for millions more. The abyssal plains would be the bottom of the ocean if the ocean floor were uniform, if the processes that shape the planet operated with perfect consistency, distributing crust and sediment evenly across the seafloor. But the Earth is not uniform. Its surface is broken into plates that move, collide, pull apart, slide past one another in a slow tectonic dance that has been ongoing for billions of years, reshaping continents, opening and closing ocean basins, building mountains and tearing them down again in cycles that span hundreds of millions of years. And where these plates meet, where they converge and one is forced beneath the other in a process called subduction, the ocean floor does not remain flat. It bends downward, folding into itself, creating long, narrow depressions that cut across the abyssal plains like scars, like wounds in the seafloor that never heal because they are active, ongoing features of a dynamic planet, constantly deepening as one plate descends beneath another, pulled down by gravity into the hot plastic mantle below. These are the oceanic trenches, and they represent the deepest parts of the ocean, the lowest points on Earth's solid surface, places where the seafloor drops away suddenly and steeply, descending thousands of meters below the already deep abyssal plains into regions that exist at the very limit of what we consider ocean, at the boundary between the hydrosphere and the lithosphere, where water and rock meet under pressures so extreme that the distinction between fluid and solid begins to blur. The trenches are not wide. Most are only a few kilometers across at their widest point, sometimes less, and they are not evenly distributed across the ocean, but concentrated in specific regions, primarily around the edges of the Pacific Ocean, where the Pacific Plate is being subducted beneath the surrounding continental and oceanic plates, in a process that creates not only trenches, but also volcanic arcs, earthquakes, and the slow recycling of oceanic crust back into the mantle from which it originally came. The deepest of these trenches, and therefore the deepest point in the ocean, is the Mariana Trench, which runs for more than 2,500 kilometers along the western edge of the Pacific, east of the Mariana Islands, in a region where the Pacific Plate is being subducted beneath the much smaller Philippine Plate at a rate of several centimeters per year. Within the Mariana Trench, there is a smaller depression called the Challenger Deep, named after the British survey ship HMS Challenger, which first measured its depth in the 1870s using weighted lines, obtaining a reading of around 8,000 meters, which seemed impossibly deep at the time, but turned out to be an underestimate. Modern sonar measurements, refined over decades of increasingly precise surveys, place the deepest part of the Challenger Deep at approximately 10,984 meters below sea level, though the exact depth varies slightly depending on where you measure and how you account for the irregularities of the seafloor. The fact that even at these depths, the bottom is not perfectly smooth, but includes small hills and valleys, minor variations in elevation that matter when you are trying to determine the absolute lowest point. To reach this depth, to actually descend to the bottom of the Challenger Deep, requires specialized equipment capable of withstanding pressures that exceed 1,090 atmospheres, more than 16,000 pounds per square inch, enough to compress styrofoam to a fraction of its original size, to implode hollow objects almost instantly, to kill any surface organism within seconds if not protected by a pressure hull. Only a handful of manned submersibles have ever made the descent, the bathyscaphe Trieste in 1960, carrying Jacques Piccard and Don Walsh, and more recently, the Deep-Sea Challenger in 2012, piloted by filmmaker James Cameron, along with a few other missions in the years since, each one representing a monumental engineering achievement, a test of materials and design pushed to their absolute limits. And even with all this effort, the total time humans have spent at the bottom of the Challenger Deep amounts to only a few hours, a few brief visits spread across more than 60 years, during which they saw very little, a flat, muddy bottom, a few small organisms, mostly amphipods and sea cucumbers. The same kinds of creatures found elsewhere on the abyssal plains, but adapted to survive at even greater depths, under even more extreme conditions. What makes the trenches remarkable is not just their depth, but what they represent in terms of planetary mechanics. A trench is not a static feature, not a hole that was dug and then left alone, but an active zone where the seafloor is being consumed, where old oceanic crust, formed millions of years ago at mid-ocean ridges, is being pulled back down into the mantle, heated and compressed until it partially melts, contributing to the magma that eventually rises back to the surface through volcanic arcs, completing a cycle that takes roughly 200 million years from formation to subduction to recycling. The trench marks the beginning of this descent, the place where the plate first bends downward, where the ocean floor starts to leave the ocean and enter the solid earth, crossing a boundary that is normally invisible but becomes visible here, at the edges of continents, where the two great geological processes, seafloor spreading and subduction, meet and interact. And this has profound implications for understanding depth, because it means that the deepest parts of the ocean are not deep because water pooled there, not because some depression in the seafloor happened to fill with more water than elsewhere, but because the seafloor itself is being pulled down, because the bottom is literally sinking, descending into the planet, and the water is simply following, filling the space left behind as the crust bends and breaks and slides beneath the adjacent plate. The depth of the trenches is a function of geology, of the forces that move continents and open ocean basins, of processes that operate on timescales measured in millions of years, but which produce, in the present moment, these extraordinary vertical distances, these places where the planet's surface drops away into abysses that challenge our ability to comprehend scale, that push the limits of human engineering and endurance, that exist as reminders of how much of Earth remains unexplored, unreachable, fundamentally alien to the surface world where we live. At these depths, time itself seems to operate differently, not in the literal sense. A second is still a second, an hour still an hour, but in the sense that the processes which define time's passage, the changes and transformations that mark one moment as distinct from another, slow down so dramatically that the deep ocean begins to feel less like a place where events happen, and more like a place where events are suspended, held in a kind of permanent present that stretches across decades or centuries without noticeable alteration. On land, we experience time through decay and growth, through the turning of seasons, through the visible aging of buildings and trees and mountains worn slowly to sand by wind and water. But in the deep ocean, where temperatures remain constant, where there are no seasons, where light never penetrates and oxygen levels are often low, decay happens at a pace so reduced that organic matter can persist for years or decades without decomposing, preserved by cold and pressure and the absence of the bacteria that normally break down dead tissue within days or weeks. This creates a strange kind of archive, an accumulation of traces that would vanish quickly elsewhere, but which remain visible in the deep ocean for extraordinarily long periods. A whale carcass that sinks to the abyssal plains does not disappear overnight. It becomes what marine biologists call a whale fall, a temporary ecosystem that can last for decades as scavengers slowly consume the soft tissue, as bacteria colonize the bones and extract the lipids stored within them, as specialized organisms, worms, clams, mussels, take up residence in the skeleton and feed on the chemical energy released by bacterial decomposition. The entire process can take 50 years or more, depending on the size of the whale and the depth at which it comes to rest. And during that time, the whale fall serves as an oasis of concentrated nutrients in an otherwise nutrient-poor environment, supporting a community of organisms that could not survive without it, that depend on these rare, unpredictable inputs of energy from the surface world. And when the whale fall is finally exhausted, when the last of the organic matter has been consumed and the bones lie bare and exposed on the sediment, even then, they do not disappear. They persist, sometimes for centuries, slowly dissolving in the seawater, gradually being buried by the accumulating sediment, but remaining visible much longer than any bones would remain visible on land, where rain and wind and the activity of plants and animals would break them down, scatter them, incorporate them back into the soil within a few years. The deep ocean is not a place of rapid recycling. It is a place of preservation, where things last, where the marks left by passing organisms or falling objects can remain legible for timescales that approach the geological, where a track pressed into the soft mud by a sea cucumber might persist for years, undisturbed by currents or other animals, a fossilized trace of movement that happened long ago and may never be seen by human eyes. This is partly because the abyssal environment is so stable, so unchanging, that there are few forces capable of erasing traces once they appear. On land, erosion is constant. Rain washes away footprints, wind smooths out tire tracks, Vegetation grows over abandoned roads, returning them to wilderness within a human lifetime. But on the abyssal plains, there is no rain, no wind, no vegetation, only the slow settling of sediment and the occasional passage of a bottom current, most of which are too weak to disturb the seafloor significantly. The result is that the deep ocean accumulates history in a way that the surface world does not, building up layers of evidence, tracks, feeding traces, burrows, shell fragments, the scattered remains of organisms that lived and died, that would be erased elsewhere, but which persist here, compressed into the sediment, preserved as a record of activity that can be read, if you know how to interpret it, as a narrative of life lived slowly, patiently, in a place where nothing happens quickly and nothing is forgotten. The organisms themselves seem to operate on these extended timescales, growing more slowly, reproducing less frequently, living longer than their shallow water relatives. A deep-sea sponge might add only a few millimeters to its size each year, taking decades to reach maturity, potentially living for centuries if left undisturbed. A deep-sea fish might not reproduce until it is 10 or 15 years old, producing only a few offspring over its lifetime, investing heavily in each one because the chances of survival are so low and the cost of reproduction so high. A deep-sea clam, living at a hydrothermal vent or cold seep, might grow so slowly that its age can be measured in centuries, with some individuals estimated to be 200 years old or more, making them among the longest-lived animals on Earth. Though their longevity is less a triumph than a necessity, a consequence of living in an environment where energy is so limited that rapid growth and reproduction are simply not possible. What this suggests is that depth and time are intimately connected, that the deeper you go, the more the ocean begins to resemble a geological system rather than a biological one, where the relevant timescales are not days or years, but centuries and millennia, where the pace of change is so slow that it becomes invisible except when viewed across vast stretches of time. A sediment core pulled from the abyssal plains shows this clearly. Each layer represents not a season or a year, but thousands of years, sometimes tens of thousands, compressed into a few centimeters of mud that looks, to the untrained eye, uniform and featureless, but which contains, encoded in its chemistry and its fossil content, a record of ocean temperatures, of atmospheric CO2 levels, of volcanic eruptions and ice ages, and the long, slow oscillations of Earth's climate over hundreds of thousands of years. And this has a curious psychological effect, because it means that the deep ocean exists in a different temporal register than the surface world, that to think about the abyssal plains or the trenches is to think about processes that are so slow they cannot be observed directly, only inferred, extrapolated from measurements taken decades apart, from growth rings in coral skeletons or sediment layers in cores, from the accumulation of tiny changes that add up over geological time to something significant. It requires a kind of patience, an acceptance that understanding depth means accepting that most of what happens there happens too slowly to see, that the relevant unit of measurement is not the human lifetime, but the million year, not the generation, but the epoch, and that this slowness is not a limitation, but a fundamental characteristic of the environment, a consequence of the physical conditions, the cold, the pressure, the darkness, that make the deep ocean what it is. To survive at depth requires more than tolerance for pressure and darkness. It requires a fundamental reimagining of what a body can be, what metabolic processes are possible, what strategies can sustain life when almost all the assumptions that govern surface biology no longer apply. The creatures that live in the deep ocean are not simply modified versions of shallow water organisms, not fish or invertebrates that have been tweaked slightly to handle a harsher environment. They are something else entirely, shaped by selective pressures so different from those at the surface that they have evolved into forms that seem, at first glance, almost alien, almost incompatible with the idea of life as we usually understand it. And yet they are alive, metabolizing, growing, reproducing, navigating their environment with senses and behaviors that are perfectly adapted to conditions we would find immediately lethal. Consider the body plan of a typical deep-sea fish. It is not streamlined in the way surface fish are, not built for speed or agility, because there is no need for either in an environment where food is scarce and energy must be conserved. Instead, the body is often soft, gelatinous, with reduced bone structure and muscles that are barely developed, just enough to allow slow movement, but no more. The skin is thin, sometimes transparent, because there is no light to hide from and no predators that hunt by sight. The swim bladder, if it exists at all, is filled not with gas, but with lipids, with oils that are less compressible than air and that allow the fish to maintain neutral buoyancy without the risk of rupture that a gas-filled bladder would pose under high pressure. Some deep-sea fish have no swim bladder at all, simply drifting with the currents or resting on the seafloor, conserving energy by moving as little as possible, waiting for prey to come within reach rather than actively hunting. The mouth is often disproportionately large, sometimes hinged in ways that allow it to open far wider than seems anatomically possible, because when food does appear, and it appears rarely, the opportunity must not be wasted. A deep-sea anglerfish, for instance, can swallow prey larger than itself, its jaw dislocating, its stomach expanding to accommodate meals that might need to last for weeks or months. The teeth are long, needle-like, angled backward to prevent escape because once something is caught, it cannot be allowed to slip away. And in many species, particularly the anglerfish, there is the lure, the bioluminescent appendage that dangles in front of the mouth like bait on a fishing line, glowing softly in the darkness, attracting smaller fish that mistake it for food or for a potential mate, drawing them close enough that the anglerfish can strike, fast and sudden, the only moment of speed in an otherwise motionless existence. But perhaps the strangest adaptations are not anatomical, but biochemical, the invisible changes that occur at the molecular level to allow cells to function under pressures that would denature most proteins, that would disrupt the lipid membranes that hold cells together, that would make metabolic processes impossible. Deep-sea organisms produce specialized molecules, osmolytes, chaperone proteins, modified lipids that stabilize their cellular machinery under pressure, that prevent their enzymes from unfolding, that keep their membranes fluid and functional even in cold water and crushing pressure. These are adaptations that cannot be seen, that leave no trace in the fossil record, but which are as essential to survival at depth as eyes are to survival at the surface. Perhaps more so, because without them, the organism would die regardless of how well its body is shaped for the environment. And then, there are the organisms that live not on the organic matter that falls from above, but on chemical energy, on the compounds that seep up from beneath the seafloor at hydrothermal vents and cold seeps, places where the Earth's interior breaks through to the ocean floor and releases hydrogen sulfide, methane, and other reduced chemicals that would be toxic to most surface life, but which serve as fuel for chemosynthetic bacteria, organisms that can extract energy from these chemicals. The way plants extract energy from sunlight. These bacteria form the base of entire ecosystems that exist independently of the sun, that draw their energy not from photosynthesis, but from geochemistry, from the slow oxidation of minerals and gases rising from deep within the planet. Around these vents and seeps, you find dense aggregations of life, tube worms that grow several meters long, mussels and clams that cluster by the thousands, crabs and shrimp that feed on the bacteria or on each other, all of them thriving in conditions that would seem inhospitable, thriving precisely because those conditions exist, because they have found a way to exploit an energy source that no other organisms can access. The tube worms are particularly remarkable. They have no mouth, no digestive system, no way to consume food in the conventional sense. Instead, they house colonies of chemosynthetic bacteria within their tissues, in a specialized organ called a trophosome, and these bacteria produce organic compounds that the worm absorbs and uses for energy. The relationship is symbiotic, mutualistic. The worm provides the bacteria with access to hydrogen sulfide from the vent water and oxygen from the surrounding seawater. both of which the bacteria need to generate energy. And in return, the bacteria provide the worm with nutrition, with the sugars and amino acids it needs to grow and reproduce. The worm, in effect, is a living container for a bacterial culture, its entire body organized around the task of maintaining optimal conditions for its symbionts, of delivering the raw materials they need and removing the waste products they generate, a partnership so complete that neither organism could survive without the other. What makes these adaptations so profound is not just that they work, but that they suggest how flexible life is, how capable it is of finding solutions to problems that seem, from a surface perspective, insurmountable. Pressure, darkness, cold, scarcity. These are not barriers to life, but simply parameters, constraints within which life can operate if given enough time to adapt. If selective pressure is strong enough, and genetic variation provides the raw material for natural selection to work with. The deep ocean is not a marginal environment, not a place where life barely hangs on at the edge of possibility. It is a fully realized biosphere, complete and functional, with its own energy sources, its own food webs, its own ecological relationships, all of it operating according to principles that are different from those at the surface, but no less valid, no less successful in evolutionary terms. In the absence of light, other senses become primary, other ways of perceiving the environment take precedence, and in water, where sound travels much faster and farther than it does in air, hearing becomes not just useful, but essential, the primary means by which many organisms navigate, communicate, find food, avoid predators, and locate mates across distances that would be impossible to traverse by any other means. Sound in water moves at roughly 1,500 meters per second, more than 4 times faster than sound in air, and under the right conditions, it can travel for hundreds or even thousands of kilometers without significant loss of energy, propagating through the ocean like ripples spreading across a pond, except the pond is the size of an ocean basin, and the ripples are pressure waves that carry information encoded in their frequency, their amplitude, their timing, their pattern. This creates what might be called an acoustic landscape, a 3-dimensional space defined not by what you can see, but by what you can hear, where objects and organisms announce their presence through the sounds they make, where distance is judged by the time it takes for an echo to return, where the texture of the seafloor can be inferred from the way sound reflects off it, where predators can be detected by the vibrations they produce as they move through the water, where prey can be located by the faint sounds they make while feeding or swimming. For creatures that live in total darkness, this acoustic landscape is as detailed and information-rich as the visual landscape is for surface-dwelling organisms, perhaps more so, because sound penetrates darkness effortlessly, passes through water with minimal scattering, and carries further than light ever could even in the clearest water. Whales in particular have become masters of this acoustic space, developing vocalizations that can travel across entire ocean basins, crossing thousands of kilometers of open water to reach other whales, communicating information, location, reproductive status, perhaps even individual identity, that would be impossible to convey by any other means at such distances. The songs of baleen whales, particularly fin whales and blue whales, are among the loudest sounds produced by any living organism, reaching intensities of up to 180 decibels or more, loud enough that they can be detected by hydrophones on the opposite side of an ocean, loud enough that they constitute a kind of long-distance communication network, a way for whales to remain connected, even when separated by distances that would take days or weeks to swim. The songs are low frequency, typically below 100 Hz, sometimes below 20 Hz, which is below the threshold of human hearing, but which travels extraordinarily well through seawater, especially at depths where the ocean forms what is called the seafloor channel, a layer of water where temperature and pressure create conditions that allow sound to propagate with minimal loss over vast distances. The seafloor channel, which stands for sound fixing and ranging, exists at depths between roughly 600 and 1200 meters in most parts of the ocean, though the exact depth varies with latitude and water temperature. It forms because sound speed in water depends on both temperature and pressure. Warmer water carries sound faster, and higher pressure also increases sound speed. And at a certain depth, These two factors balance in such a way that sound waves emitted at that depth are refracted back toward the channel rather than spreading outward, effectively trapping the sound and guiding it horizontally through the ocean like light through a fiber optic cable. Whales seem to instinctively understand this, diving to depths where their vocalizations will enter the SOFAR channel and propagate efficiently, maximizing the range of their communication without expending additional energy, using the ocean's acoustic properties the way radio broadcasters use the ionosphere to bounce signals over the horizon. But the ocean is not always noisy. There are long stretches of silence, long periods when no whales are singing, when no ships are passing overhead, when the only sounds are the faint ambient noise of waves breaking at the surface far above, the occasional click of a shrimp, the low rumble of a distant earthquake, or the creaking of ice shelves as they shift and calve. This silence is not the absence of sound, but a different kind of acoustic environment, one where sound is rare enough that each occurrence stands out, where a single vocalization can be heard clearly because there is nothing to mask it, nothing competing for the same acoustic space. For organisms that rely on sound, this silence is both a challenge and an opportunity. A challenge because it makes them more detectable when they do make noise, more vulnerable to predators that might be listening, but an opportunity because it means that signals, when transmitted, are likely to reach their intended recipients without interference, without being drowned out by background noise. Some organisms have adapted to produce sounds so specific, so precisely tuned, that they can communicate over short distances without alerting others. Certain species of fish produce low-frequency clicks or grunts that travel only a few meters before dissipating, allowing them to communicate with nearby individuals, perhaps to coordinate spawning, perhaps to establish territory, without broadcasting their presence to the entire acoustic landscape. Dolphins and toothed whales use echolocation, emitting rapid sequences of high-frequency clicks and listening for the echoes that bounce back, building up a detailed acoustic image of their surroundings, able to detect the size, shape, distance, and even internal structure of objects and organisms around them with a precision that rivals or exceeds visual perception in clear water. The clicks are highly directional, focused into a beam by specialized structures in the whale's head, which means that the echolocation is private, targeted, less likely to be overheard by unintended listeners than a broadcast vocalization would be. And then there are the sounds that are not biological, but geological. The deep rumblings and groans of the earth itself as tectonic plates shift, as underwater volcanoes erupt, as landslides cascade down continental slopes, as icebergs carve from glaciers and crash into the sea. These sounds are often infrasonic, below the range of human hearing, but detectable by sensitive instruments, and they travel for enormous distances, propagating through the ocean and even through the solid earth, carrying information about geological activity that might otherwise go unnoticed. Seismologists use arrays of underwater microphones to monitor these sounds, to detect earthquakes, to track volcanic eruptions, to study the processes that shape the seafloor, and in doing so they have discovered that the ocean is far from silent, that it is filled with sounds at frequencies both below and above the range of human perception. A complex acoustic environment that is constantly active even if it appears, to us, to be quiet. What this means is that the deep ocean is simultaneously silent and full of sound, empty and crowded, depending on what you are listening for and how sensitive your hearing is. A paradox that reflects the fact that human perception is limited, adapted for life on land where sound behaves differently and where vision is the dominant sense. For most of human history, the deep ocean was not just unexplored, but unexplorable. Not a place humans could go, but simply a blank space on maps, a region marked only by its absence of information, by the fact that ships could sail across its surface, but could tell you nothing about what lay beneath, except that it was deep and dark, and presumably empty of anything that mattered to surface-dwelling civilizations. The technology to descend beyond a few meters did not exist. A diver holding their breath could reach perhaps 20 or 30 meters, maybe 40 if they were exceptionally trained and willing to risk their life. But beyond that, the pressure became too great. the need for air too urgent, the darkness too complete. And even if you could somehow survive the descent, there was no guarantee you could return, no way to ascend quickly without suffering decompression sickness. The bends, as nitrogen dissolved in your blood under pressure, came out of solution too rapidly on the way up, forming bubbles that blocked circulation, that caused pain and paralysis and sometimes death. The invention of diving bells and later diving suits extended this range somewhat, allowing humans to descend while breathing air supplied from the surface. But these were tethered devices, limited by the length of their air hoses and the fact that they still required the diver to breathe compressed air, which meant that time at depth was limited by nitrogen narcosis, by oxygen toxicity, by the need to decompress slowly on the way back up to avoid injury. By the mid-20th century, it was possible for divers to reach depths of a few hundred meters, but this required extensive training, elaborate equipment, and careful planning. And even then, the time that could be spent at depth was measured in minutes, not hours, because the deeper you went, the more compressed air you breathed, and the more nitrogen dissolved in your tissues, requiring longer and longer decompression stops on the return to the surface. The ocean floor, at 3,000 or 4,000 meters, remained as inaccessible as ever, beyond the reach of any diver, beyond the limits of any tethered system. What changed this was the development of submersibles, small, self-contained vessels with pressure hulls capable of withstanding the enormous forces at depth, carrying their own power supply, their own life support, their own means of propulsion, allowing them to descend untethered, to move freely across the seafloor, to remain at depth for hours without the need for continuous connection to the surface. The first true deep-diving submersible was the bathysphere, a spherical steel chamber lowered on a cable, which reached depths of 900 meters in the 1930s, carrying naturalist William Beebe and engineer Otis Barton into the twilight zone, where they observed bioluminescent creatures and described the color of the water as it shifted from blue to violet to black. But the bathysphere was still tethered, still dependent on the cable for lowering and raising, and it could not move horizontally, could not explore, only descend and ascend along a fixed vertical path. The breakthrough came with the bathyscaphe, a free-diving submersible that used gasoline for buoyancy, gasoline being lighter than water and less compressible than air, and iron ballast for weight, allowing it to sink by gravity and rise by releasing the ballast, eliminating the need for a cable and giving it the ability to descend to any depth, limited only by the strength of its pressure hull. The bathyscaphe Trieste, built in the 1950s and later acquired by the US Navy, made its historic descent to the bottom of the Challenger Deep in 1960, carrying Jacques Piccard and Don Walsh to a depth of 10,900 meters, deeper than any human had gone before or would go again for more than 50 years. The descent took nearly 5 hours, sinking slowly through the water column, passing through the twilight zone, into the midnight zone, into the abyssal zone, and finally into the hadal zone, the deepest part of the ocean, named after Hades, the Greek underworld, because it seemed at the time as remote and unreachable as any mythological realm. What they saw at the bottom was at once underwhelming and profound. The seafloor was flat, covered in a fine sediment that looked grey in the lights of the bathyscaphe, featureless except for small tracks and burrows left by unseen organisms. They observed a flatfish, a sole, or a flounder lying on the bottom, which was remarkable because it suggested that even at these depths, even under more than 1,000 atmospheres of pressure, complex vertebrate life could exist, could function, could go about its business as if the weight of 7 miles of water above it were irrelevant. But they could not stay long. The bathyscaphe had only enough battery power for a few hours at depth, and the return to the surface would take another 3 hours, rising slowly through the darkness, the pressure decreasing gradually as they ascended, until finally they broke through the surface and could open the hatch and breathe fresh air again, having touched the bottom of the world and returned to tell about it. Since then, only a handful of other descents have been made to the Challenger Deep, each one a major expedition requiring years of planning and millions of dollars in funding, each one lasting only a few hours at the bottom before the need to conserve power or the limits of the life support system required a return to the surface. James Cameron's descent in 2012 in the submersible Deep-Sea Challenger was the first solo dive to the bottom and included high-definition cameras that captured footage of the seafloor in far greater detail than had been possible during the Trieste mission. But even then, the time at depth was limited. The area explored was small, a few hundred meters at most, a tiny fraction of the trench floor, which extends for more than 2,000 kilometers and remains almost entirely unmapped. Unexplored, unknown, except through indirect measurements made by sonar from ships at the surface. What these missions reveal is not just that the deep ocean is difficult to explore, but that it actively resists exploration. That the conditions at depth, the pressure, the darkness, the cold, the sheer distance from the surface, impose limits on how long humans can remain, how much they can see, how thoroughly they can investigate. Each descent is a brief visit, a snapshot, a few hours of observation followed by a long return journey, and what is learned must be extrapolated, generalized, used to infer conditions across vast regions that will likely never be visited directly, that will remain known only through the imperfect lens of remote sensing and the occasional lucky sample retrieved by unmanned vehicles. The paradox of ocean exploration is that we have mapped the surface of Mars in higher resolution than we have mapped our own ocean floor, have sent rovers to investigate Martian rocks and soil with more thoroughness than we have applied to most of the abyssal plains, have devoted more resources and attention to understanding a planet that lies hundreds of millions of kilometers away than to understanding the depths that begin just a few kilometers beneath the surface of our own world. This is not because Mars is more interesting, though it may be, or because the ocean is less important, though that argument is sometimes made, but because Mars is easier to study, because it can be observed from orbit, because light reflects off its surface and returns to cameras and spectrometers and radar systems in ways that allow us to build detailed maps, to identify geological features, to track changes over time without ever needing to land on the surface. The ocean does not cooperate in this way. It absorbs light, hides its floor beneath kilometers of opaque water, reveals itself only through indirect methods, sonar, gravity measurements, magnetic surveys, that provide low-resolution data, rough approximations, maps that show the large-scale features, but miss almost everything smaller than a few hundred meters across. Current estimates suggest that we have mapped approximately 20% of the ocean floor at high resolution, with high resolution defined as anything approaching the level of detail we expect from terrestrial mapping, the ability to see individual features, to distinguish between a ridge and a valley, to identify the texture of the seafloor. The remaining 80% is known only through satellite altimetry, a technique that measures the height of the ocean surface from orbit and uses those measurements to infer the topography of the seafloor beneath, based on the fact that underwater mountains create slight bulges in the ocean surface due to their gravitational pull, while trenches create slight depressions. This works, in a general sense. It can identify large features like mid-ocean ridges and trenches, but it provides resolution measured in kilometers, not meters, which means that anything smaller than a large mountain or a major canyon is effectively invisible, undetectable, unknown. The ocean floor could be covered in features the size of cities, and we would not know, could contain valleys and hills and seamounts by the thousands, and they would not appear on our maps, would remain hidden beneath the low-resolution data points that constitute our current understanding of the seafloor. And this is just the topography, the shape of the bottom. It says nothing about what lives there, what ecosystems exist, what geological processes are active, what resources might be present, what historical information is preserved in the sediments. To answer those questions requires direct observation, requires sending vehicles or instruments to the seafloor, collecting samples, taking photographs, measuring temperatures and chemical compositions. And this has been done in only a tiny fraction of the ocean, probably less than 1%, possibly less than 0.1%, depending on how you define exploration. A submersible might spend a day surveying a few hundred meters of seafloor, taking samples, documenting what it finds. But the abyssal plains extend for millions of square kilometers, the trenches for thousands of kilometers, and even if we dedicated every research vessel and every submersible to systematic mapping, Even if we invested the resources needed to cover the entire ocean floor, it would take decades, possibly centuries, to complete the work. And by the time it was finished, the early surveys would be out of date, would need to be repeated to account for changes that occurred during the intervening years. This leaves us in the strange position of living on a planet whose surface is mostly unknown to us. Not unknown in the sense of being inaccessible or impossible to reach. We have the technology to go there if we choose to, but unknown in the sense of not having been looked at, not having been surveyed, not having been incorporated into the collective understanding of what Earth is and how it works. There are regions of the abyssal plains larger than continents that no human has ever seen, that no camera has ever photographed, that are known only as depth contours on low-resolution maps, as numbers indicating how far down the bottom is, but saying nothing about what the bottom looks like, what it is made of, what moves across it or burrows into it. There are seamounts, underwater mountains that rise thousands of meters above the surrounding seafloor, that were discovered only recently, despite being enormous geological features, simply because no one had looked there before, because the ocean is so vast and the resources available for exploration so limited that we are still finding large-scale features, still filling in gaps in our knowledge that would be considered basic information if we were talking about land. And this raises a question that has no satisfying answer, which is why we have not prioritized ocean exploration the way we have prioritized space exploration, why images from Mars receive more public attention than images from the abyssal plains, why the discovery of water on a distant moon generates more excitement than the discovery of a new hydrothermal vent ecosystem on Earth. Part of the answer is accessibility. Space can be seen, can be photographed, can be observed by anyone with a telescope, whereas the deep ocean is invisible, hidden, available only through expensive expeditions that produce data but not spectacle, information but not inspiration. Part of the answer is cultural. The fact that space has always occupied a special place in human imagination has been associated with exploration and adventure and the frontier, whereas the ocean is familiar, taken for granted, assumed to be understood even when it is not. And part of the answer is practical. Space exploration, despite its costs, has produced technologies and spin-offs that justify the investment in ways that ocean exploration has not, at least not in ways that are immediately visible or easily monetized. But there is something troubling about this imbalance, something that suggests a kind of willful ignorance, a decision to look outward rather than downward, to focus on distant possibilities rather than immediate unknowns. The deep ocean is not a marginal environment. It is the largest habitat on Earth, covering more than half the planet's surface, containing more volume than all terrestrial ecosystems combined. And yet, it remains largely unexplored, largely unmapped, a blank space in our understanding of the world we live on. What lies beneath the surface is not empty space waiting to be filled, but a complex, active, biologically rich environment that we are only beginning to understand, and the fact that we know so little about it, that we have chosen to invest our curiosity and our resources elsewhere, says something about how we see ourselves, about what we value, about where we imagine our future lies. To live on a planet and not know it completely is not unusual. No species has ever had complete knowledge of its environment, and humans are no exception. But what is unusual is to be aware of this incompleteness, to know that large portions of the planet remain unexplored, to have the cognitive capacity to imagine what might be there, and the technological capability to go and look, and yet to choose, mostly, not to. This creates a peculiar state of knowing and not knowing simultaneously, where we understand that the ocean floor exists, that it has topography and ecosystems and geological processes, but where we lack the specific information that would make that understanding concrete, that would transform it from abstract knowledge into detailed familiarity. We know there are seamounts we have never mapped, species we have never catalogued, geological events we have never witnessed, but we do not know where exactly they are, what they look like, how they function, what role they play in the larger systems that govern the planet. This unknowing is not neutral. It has consequences, both practical and philosophical, that extend beyond the simple absence of information. Practically, it means that we make decisions about ocean management, about fishing and mining and conservation, based on incomplete data, on models and extrapolations that may or may not reflect what is actually happening on the seafloor. We designate marine protected areas without knowing exactly what we are protecting, establish fishing quotas without fully understanding the ecosystems from which we are extracting resources, plan deep-sea mining operations without detailed knowledge of what organisms live in the areas we intend to disturb, or how those ecosystems might respond to disruption. The absence of information forces us to proceed with uncertainty, to make choices that might turn out to be reasonable or might turn out to be catastrophic, and we will not know which until after the fact, until we have either succeeded in preserving something valuable or destroyed something we did not realize was there. Philosophically, the unknowing raises questions about what it means to inhabit a world, about whether true inhabitation requires knowledge or whether it is possible to live somewhere without understanding it, to move across a surface while remaining ignorant of what lies beneath. For most of human history, this was not a question anyone asked, because the limits of exploration were accepted as natural and insurmountable, because no one expected to know what was at the bottom of the ocean any more than they expected to know what was inside the Earth or beyond the edge of the atmosphere. But now that we have the capacity to explore, now that we have sent humans to the moon and robots to Mars and probes beyond the solar system, the fact that we have not explored our own ocean with similar thoroughness begins to feel like a choice, like a deliberate turning away from something that might be uncomfortable or inconvenient, or simply too large to comprehend. And perhaps that is part of what makes the deep ocean so difficult to think about. Not that it is physically inaccessible, though it is, but that it is psychologically overwhelming, that it represents a kind of depth that human consciousness is not well equipped to process. We are surface creatures, adapted to navigate two-dimensional landscapes where up and down are fixed and obvious, where we can see to the horizon and judge distances by eye, where the world is divided neatly into land and sky, and the boundary between them is clear. The ocean disrupts this simplicity, introduces a third dimension that extends downward for miles, creating volumes so large that they dwarf the terrestrial world, and doing so beneath a surface that looks, from above, unremarkable, indistinguishable from any other body of water. The disconnect between what the ocean appears to be and what it actually is creates a kind of cognitive dissonance, a failure of intuition that makes it difficult to hold the ocean in mind as a real place rather than as an abstraction. This is compounded by the fact that the deep ocean offers no sensory feedback, no immediate experience that would make its existence feel tangible. You cannot see it unless you descend into it, and even then you see only a small sphere of illuminated water surrounded by darkness. You cannot hear it except through specialized equipment that translates underwater sounds into frequencies we can perceive. You cannot touch it without being crushed by it. It exists as data, as numbers and charts and photographs taken by robots. And while data can be convincing, it does not produce the same visceral understanding that direct experience does not create the emotional connection that might motivate deeper exploration or more sustained attention. The ocean remains abstract, distant, theoretical, even when we know intellectually that it is the largest and most important feature of the planet's surface, even when we understand that our lives depend on it in ways both obvious and subtle. And so the ocean remains, for the most part, unexplored, not because exploration is impossible, but because it is difficult and expensive and yields knowledge that does not immediately translate into economic or political advantage, that does not satisfy the human preference for narratives with clear beginnings and endings, for discoveries that can be photographed and shared and celebrated. The deep ocean does not lend itself to such narratives. It is too vast, too slow, too dark, too uniform in some ways, and too complex in others. And the knowledge it offers is accumulative rather than revelatory, building up slowly through decades of patient work rather than arriving in sudden breakthroughs. This makes it hard to fund, hard to popularize, hard to sustain public interest in. And the result is that much of what we know about the deep ocean comes from incidental observations, from research conducted for other purposes, military sonar mapping, undersea cable surveys, oil exploration, rather than from systematic scientific investigation aimed at understanding the ocean for its own sake. What we are left with, then, is a planet that is simultaneously known and unknown, mapped and unmapped, a place where we can predict the weather with reasonable accuracy, but cannot tell you what lies in most of the ocean, where we can track satellites in orbit, but cannot say with certainty what geological processes are occurring on the abyssal plains, where we have catalogued millions of species, but estimate that millions more remain undiscovered, most of them in the ocean, most of them at depths we have barely begun to explore. But to know that something exists beyond our direct experience, to know that beneath every ocean's surface there are kilometers of water pressing down on darkness and cold and life that continues without reference to the world above. This knowledge does something to consciousness, changes the way you think about where you are when you stand at the shore or swim in coastal waters or cross an ocean by plane. It introduces a vertical dimension to places that had seemed flat, two-dimensional, knowable by their surface characteristics alone. The ocean, once you become aware of its depth, stops being simply water and becomes instead a volume, a space that extends downward farther than most terrestrial distances extend horizontally, a hidden landscape that is always there beneath you when you float or swim or sail, pressing up from below with a weight that you do not feel, but which exists nonetheless, mathematically, physically, as tons per square inch increasing with every meter of depth. This awareness can be unsettling, particularly for those who spend time on or in the water, who must navigate its surface while knowing that the surface is only the thinnest boundary, a membrane between breathable air and an environment that would kill them within minutes. Sailors speak of this sometimes, the feeling of moving across water that might be 3 or 4 kilometers deep, of knowing that if the ship were to sink, it would fall for an hour or more before reaching the bottom, descending through zones of decreasing light and increasing pressure until it came to rest on the abyssal plains, where it would remain, largely undisturbed, for centuries or millennia, slowly being covered by sediment, becoming part of the geological record, a layer in the archive of human history that would be readable, theoretically, by anyone with the technology to descend and look. Swimmers sometimes experience something similar, a moment of vertigo when they realize that their feet are dangling over depths they cannot see or fathom, that the water beneath them extends down beyond any distance they could swim, beyond any depth they could dive to and return from safely. This is not quite fear, though it can become fear, particularly in those who are already uncomfortable in deep water. It is more like a recalibration of scale, a sudden recognition that the environment they are in is far larger and stranger than it appears from the surface, that they are not swimming in a pool or a lake where the bottom is visible and the boundaries are clear, but in an ocean that has no meaningful bottom from their perspective, no boundary except the distant shore, no fixed point except the surface itself. And the surface, they realize, is not fixed at all, but constantly moving, rising and falling with waves and tides, shifting position relative to the seafloor below, which remains stable and unmoving while the entire column of water above it oscillates gently, responding to the pull of the moon and the push of the wind and the slow circulation of currents that move water horizontally across thousands of kilometers while barely affecting the depths below. For those who have descended, who have been in submersibles or diving bells, or who have free dived to depths where the surface light begins to fade, the awareness of depth becomes more concrete, less abstract, tied to sensory experience rather than to intellectual understanding. They describe the descent as transformative, not in the sense of changing who they are, but in the sense of changing how they perceive scale, how they think about distance and space, and the relationship between surface and depth. To descend is to move through a gradient of light and temperature and pressure that provides continuous feedback, that reminds you at every meter how far you have come and how much farther there is to go, that makes depth feel like a journey rather than a measurement, like something you travel through rather than something that is simply there. And the return to the surface, when it comes, feels less like ending a journey and more like returning from another world, crossing back over a boundary that is invisible but absolute, emerging into light and warmth and air that suddenly feel precious, remarkable, not to be taken for granted. This experience does not translate easily into words, which is perhaps why accounts of deep dives often focus on technical details: the equipment used, the procedures followed, the observations made, rather than on the subjective experience of being there, of existing temporarily in an environment so different from the surface that it requires a complete recalibration of what you consider normal. But those who have made the descent carry something back with them, a sense of having touched something fundamental about the planet, about the way it is structured, about the enormous volumes of space that exist hidden beneath surfaces we cross casually without thinking about what lies below. They become, in a sense, ambassadors from the depths, translators of an experience that most people will never have directly, but which affects everyone, because the ocean is not separate from the surface world, but intimately connected to it, driving weather patterns, regulating climate, producing oxygen, absorbing carbon dioxide, supporting food webs that extend from the deepest trenches to coastal waters to human dinner tables. And perhaps this is what makes depth matter, even for those who never leave the surface, who never descend beyond snorkeling depth, or who never enter the water at all. That the ocean, in its depth, is not a curiosity or an abstraction, but a functional component of the planetary system. One that operates largely out of sight, but which shapes conditions at the surface in ways both obvious and subtle. The temperature of surface water depends on the circulation of deep water, on the slow, overturning currents that bring cold water up from the abyss and warm water down from the tropics, mixing and exchanging heat in patterns that influence regional climates, that determine whether coastlines are temperate or tropical, whether currents are warm or cold, whether fish populations thrive or collapse. The chemistry of the ocean, its salinity, its pH, its concentration of nutrients, is regulated in part by processes that occur at depth, by the settling of organic matter, by the dissolution of minerals, by the activity of microorganisms that live in the sediments and the water column, processing compounds and releasing byproducts that eventually make their way back to the surface. To understand the ocean only as surface, then, is to misunderstand it fundamentally, to mistake the visible part for the whole, the accessible for the complete. The ocean is its depth as much as it is its surface, and the two cannot be separated except artificially, for convenience of description. And perhaps, after descending through all these layers, through the zones of fading light and increasing pressure, through the midnight regions where bioluminescence flickers briefly against absolute darkness, through the abyssal plains where time moves at geological speeds, and the sediment accumulates in silence, down to the trenches where the seafloor folds into itself, and the planet's interior begins its slow journey back toward the surface. Perhaps the most honest thing to say is that depth remains, in some essential way, unknowable, not because we lack the technology to measure it or the submersibles to reach it, but because the human mind, adapted as it is for life on surfaces, for horizontal distances and visible horizons, cannot fully internalize what it means for the ocean to extend downward for 7 miles, for water to exist under pressures that would crush steel, for ecosystems to function without sunlight, for life to continue in conditions we consider fundamentally hostile. We can measure depth, can map it, can descend into it and return with data and photographs and samples, but the experience of depth, the weight of it, the darkness of it, the cold indifference of it, remains something that resists complete translation into terms the surface world understands. There is a kind of humility in this, a recognition that some things are too large or too strange or too removed from ordinary experience to be fully grasped, and that this is not a failure but simply a fact, one that might even be valuable, a reminder that the world contains spaces that exceed our capacity to know them completely, that exist on scales and timescales that render human presence brief and peripheral. The ocean does not need to be understood to continue being what it is. It operated for billions of years before humans evolved, will continue operating long after we are gone, circulating and mixing and supporting life in the depths, whether anyone is watching or not, whether anyone descends to observe or remains on the surface, whether the trenches are mapped in high resolution or left as rough approximations on low-resolution charts. The ocean's indifference to human attention is not hostility, but neutrality, the neutrality of a system so large and self-sufficient that it does not require external validation, that simply is, regardless of whether anyone notices. And yet, to stand at the shore at night, as we might have at the beginning of this consideration, to look out across the dark water and know that beneath the surface there are kilometers of depth, entire landscapes hidden in permanent darkness, creatures moving slowly through cold water, sediments accumulating at rates too slow to observe. To hold all of this in mind simultaneously is to experience something close to what might be called planetary awareness, a sense of being part of a system that extends far beyond the visible, the accessible, the immediately comprehensible. The surface is still there, still calm or rough depending on the wind, still reflecting whatever faint light reaches it from the stars or the moon. The waves still break gently against the shore, the rhythm unchanged, indifferent to how much or how little we understand about what lies beneath them. And perhaps that is enough, to know that depth exists, to acknowledge it without needing to master it, to allow it to remain mysterious while still recognizing it as real, as present, as fundamentally connected to the world we inhabit, even when we cannot see or touch or directly experience it. The ocean, in the end, asks very little of us, only that we acknowledge its existence, its scale, its depth, and perhaps that we approach it with something resembling respect, the kind of respect you might offer to any place that has been here longer than you have and will remain after you are gone, that operates according to its own logic and its own timescales, and does not bend itself to accommodate human preference or understanding. To descend into it is a privilege, not a right, and those who have made the journey speak of it with a kind of reverence that suggests they understand this, that they have touched something vast and ancient and fundamentally other, and have returned changed in ways they struggle to articulate, carrying with them not answers, but better questions, not certainty, but a deeper appreciation for mystery. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.